Okay, so that was my brief overview of what integration is and 2 or 3 problems it can be used to address. And now I'm going to start talking about techniques of integration. And so these are techniques for finding antiderivatives of functions. And the first one is called integration by parts. So essentially what I'm going to try and do to get integration by parts is, remember when I was computing derivatives, we had certain rules. One of them was the product rule, which was the derivative of the product of 2 functions. And so I'm just going to try and use that rule backwards to be able to evaluate an antiderivative. So let's start out with 2 functions, f of x and g of x. And they need to be continuous and integrable. Then if I looked at the product of their antiderivatives, and here it's a little bit trickier what I'm going to do with constant, because if I said f of x, if I was allowed to put an arbitrary constant there, and I did the same thing with g of x, then when I multiplied these together, I would have the constant from f of x times g of x and the constant from g of x times f of x. So for this to work, I have to choose my constant to be 0. So I'm going to take the product of these 2 antiderivatives and take its derivative using the product rule. And what I'm going to end up with is the derivative of the first function times the second, so this guy here, plus the derivative of the second function times the first. So then if I take the integral of both sides of that, well, the integral, sort of by the fundamental theorem of calculus, that's just undoing my derivative operation. So I have capital F of x times capital G of x is just going to be equal to the integrals of the 2 terms on the right-hand side. And then I'm just going to rearrange these terms to get something called the integration by parts formula. So I'm going to take this second term, move it to the left-hand side of the equation, and move the other 2 terms to the right-hand side of the equation. And now what this is telling me is that if I can break my function up into a function that I can integrate, this g of x, and a function that where I can take its derivative, then I can use this formula to evaluate this integral. So generally the idea is going to be to choose f of x and little g of x so that this final term here is something that's easy to compute. So I'm starting out over here with a capital F of x. So the easiest thing that I could ever have here would just be an x, because if I took the derivative of capital X, if capital F, if that's a constant, then I could just take this little f, the derivative of a constant, if this was x, little f of x is going to be a constant, and I can take my constant outside my integral sign, and then I would just have to integrate, that should be a little g of x. No, sorry, capital G of x, never mind. So what I'm wanting to do is choose these functions so that this integral is going to be something that's easy to evaluate. And so since I'm just stumbling over my words now, I probably should just skip ahead to an example. So here, this doesn't even look like it's something that I'm going to be able to write down as a product. But you always have a 1. So if I let my capital F of x just be this function here, log of 1 plus x, and I let my g of x be 1 plus x, then my little g of x, that's just going to be the derivative of this guy here. It's just going to be a constant. It's going to be 1. So I can write this function here as capital F of x times little g of x. So this was my integration by parts formula. And then I just go ahead and plug these functions that I've worked out here into the integration by parts formula. So capital F of x is just log of 1 plus x. G of x is equal to 1, so I didn't bother to write that down. The antiderivative of that is going to be f of x, capital F of x, times capital G of x. So that's just 1 plus x times log of 1 plus x, minus the integral of little f of x. So that's going to be the derivative of this guy here, times capital G of x, which is 1 plus x. So the capital G of x ends up on top here. The derivative of the logarithm is just 1 over the argument. So in this case, the argument is 1 plus x. So little f of x is going to be 1 over 1 plus x. And technically, I skipped a step here because I also have to use the chain rule. But the derivative of 1 plus x, we already said, was equal to 1. So it's 1 over 1 plus x times 1. And now if I look at the term on the right here, I have 1 plus x divided by 1 plus x. So that's just going to cancel each other out. So I have 1 plus x times the log of 1 plus x minus the integral just of dx. And so that integral is very easy to calculate. I just end up with x being the antiderivative. And then because I don't have limits here, I'm asking for an indefinite integral, just the antiderivative. So I'm adding on an arbitrary constant c. So generally, the bulk of the work in using this formula is looking at the original function and then trying to identify, how am I going to write that as a capital F of x and a lowercase g of x. So I want to split up that function so that this term that I get on the right-hand side, the term that I still have to integrate after I use the integration by parts formula, is going to be easy to integrate. And unfortunately, there's just not a really good way to tell you how to do that. You just have to practice, and every time you do it, you get a little bit better at seeing how you could break these things up. So suppose I want to find the antiderivative for the function x squared times log of x. So this time it's going to be a little bit simpler. I mean, this is clearly the product of two functions. So I have x squared times log of x. So let's just start there by saying log of x is going to be the f of x. And I could also choose to make x squared the f of x, and log of x to be the g of x. But I'm going to have to integrate this thing. So I want to pick that in a way where it's going to be easy to do. So the capital F of x, that's something I'm going to have to take the derivative of. And it's going to be easier to take the derivative of this than it is to integrate it. On the other hand, this is just something I can use my anti-power rule on. So that's going to be something that's probably not going to be too difficult to find an antiderivative of. So let's choose that to be the part where I'm going to have to compute the antiderivative. So if my capital F of x is log of x, and my capital G of x is 1/3 x cubed, then my little g of x is going to be x squared. And so now we can figure out what the antiderivative of this function is just by plugging these values into the integration by parts formula and hoping that we're able to integrate the term that's going to end up on the right-hand side. So let's see. Yeah, got it right this time. So the integral of capital F of x, g of x, so just plug everything in. So capital F of x, that was the log of x. The g of x is the x squared. And so my integration by parts formula tells me that I take capital F of x times capital G of x. So I get 1/3 x cubed times log of x minus the integral. And now here I have my lowercase x. So here I just have to take the derivative of this function. And back in my little dictionary slide, I had the derivative of log of x is just 1 over x. So I have 1 over x times capital G of x, which is 1/3 x cubed. And so not only is it possible to integrate, it even gets a little simpler since this 1 over x is going to cancel one of my x's in my g of x function. So I end up with 1/3 x cubed log x minus the integral of 1/3 x squared. So I can use the anti-power rule to evaluate this guy here. And I end up with 1/3 x cubed times log of x minus 1/9 x cubed. And then because I haven't put any limits on this, I'm asking just for an antiderivative, an indefinite integral, so I have to add an arbitrary constant c. And we're also going to be able to do this for definite integrals. And in practice, really, it's not going to change anything. You just use the trick to find the antiderivative. But you can actually work through it if you want to. This will probably be the one and only time you do with the limits here. So this is exactly the same setup that I had before. I have the derivative of capital F of x times capital G of x. And I'm going to integrate that over an interval a, b. So because by the fundamental theorem of calculus, this integration and differentiation, they're sort of complementary operations. This integral is going to cancel out my derivative, and I just have to then evaluate my antiderivative here at its endpoints and take the difference. So that's going to give me capital F of b times capital G of b minus capital F of a times capital G of a. And I can then just rearrange the terms. So I can use the linearity property to put this integral sign in front of this function as well. So I can write this integral of a sum as the sum of two integrals. And that gives me the integration by parts formula for a definite integral. Except I believe, oh no. Yeah, so we just end up evaluating this term here at its upper and lower endpoint. So I think this can be a little bit confusing. So if you're not getting the correct answer the first time you do this, you might want to try and use this longer formula and see if that helps you spot your mistake. And so one final example. I'll try and integrate from 1 to 3 the function x times e to the x. So again, I'm going to let the function that I'm going to have to take the derivative of be x, because when I take the derivative of that, I'm just going to get 1. That'll be something easy to work with. The function I'm going to have to integrate should be, well, e to the x. Its antiderivative is just going to be itself, so that's going to be an easy choice. And so I just have to then go ahead and plug these into the integration by parts formula. So remember on the previous slide, I had written this as f of b times g of b minus f of a times g of a. And that's exactly what I mean by this notation here. So here what I mean is take capital F of 3 times capital G of 3 minus capital F of 1 times capital G of 1. And the rest of it should be clear just because the limits are still on the integral signs. And so I'm going to get this line just by plugging in the functions I've worked out into this formula here. And so this is my capital F and my capital G. And then this one was easy to do just because it's its own antiderivative. So this is 3 times e to the third minus 1 times e to the 1. So this comes from the first term here. And then from this second term, I end up with e cubed minus e. And I can do a little bit of simplification and get the answer 2e cubed.